The word electricity may evoke an image of complex modern technology, lights, motors, electronics, and computers. But the electric force is thought to play an even deeper role in our lives. According to atomic theory, electric forces between atoms and molecules hold them together to form liquids and solids. And electric forces are also involved in the metabolic processes that occur within our bodies. Many of the forces we have dealt with so far, such as elastic forces, the normal force, the friction, and other contact forces, pushes and pulls, are now considered to result from electric forces acting at the atomic level. Gravity, on the other hand, is a separate force. The early studies on electricity date back to the ancients, but it has been only in the past 2 centuries that electricity was studied in detail. In this video, I will talk about electric charge, electric force, and electric field. The electrical nature of matter is inherent in atomic structure. Like you can see in this picture, an atom consists of a small, relatively massive nucleus in the middle with the blue and the red circles that contains particles called protons and neutrons. A proton has a mass that equals 1.673 times 10 to the negative 27 kilogram. And the neutron has a slightly greater mass. Mass of the neutron equals 1.675 times 10 to the negative 27 kilogram. Well, surrounding the nucleus is a diffuse cloud of orbiting particles that are called electrons. You can see that in yellow. An electron has a mass of 9.11 times 10 to the negative 31 kilograms. Well, like mass, electric charge is an intrinsic property of protons and electrons. And there are only 2 types of charge have been discovered, positive and negative. So a proton has a positive charge. So we can write, usually the charge we denote with the lowercase q, and we put the q of the proton is positive, and the electron has a negative charge, so q of the electron is negative. Neutron has no charge at all. Experiments reveal that the magnitude of the charge on the proton exactly equals the magnitude of the charge on the electron. The proton carries a charge of positive E, we call it E, let's put Q of proton equals positive E, that's an electron carries a charge of negative E. The SI units for measuring the magnitude of an electric charge, well, electric charge, we denote it with the lowercase e. So the SI units for measuring the electric charge is actually Coulomb. And it is denoted with the capital letter C, and E has been determined experimentally, and the value of it to be equal 1.60 times 10 to the negative 19 Coulomb. The symbol E represents only the magnitude of the charge on a proton or an electron and does not include the algebraic sign that indicates whether the charge is positive or negative. In nature, atoms are normally found with equal numbers of protons and electrons. Usually, then, an atom carries no net charge because the algebraic sum of positive charge of the nucleus and the negative charge of the electrons is zero. When an atom or any object carries no net charge, the object is said to be electrically neutral. I can write that no net charge, that means Q net, which is the sum of the positive charges. Let's say positive charges, like put like that, sum of the positive charges plus sum of the negative charges, I'm going to put that way, equals 0. Then in this case, we say that we have electrically neutral object. Charges of larger magnitude than the charge on an electron or on a proton are built up on an object by adding or removing electrons, because it's easier to remove electrons or add electrons to an object. So it's very, very hard to actually split the nucleus and take away the positive charges. So that's why in everyday life it's much more easier to use to move the electrons from the atom away or to add some electrons. So therefore, any charge of magnitude, let's say Q, I'm going to put the capital Q here, that means it's a charged object, is an integer number of electric charge, E. So equals N times E. Or maybe I should put a capital letter N in here. Which indicates as an integer number. Now, because any electric charge Q occurs in an integer number of elementary, indivisible charges of magnitude E, we say that electric charge is quantized. Let's do an example. For example, let's calculate how many electrons are there in 1 coulomb of negative charge. You can pause this video right here and try to answer this question on your own, and then continue to see how we can answer this question. Well, to answer this question, let's see what we are given. We're given that we have a charge that is negative 1 coulomb, okay? And we want to find out how many electrons go into this charge. So we know from the charge is quantized, then we can say Q equals N times the number of electrons times the electric charge. From here, I can find N equals Q over E. That equals negative 1 coulomb divided by, we found electric charge on the top of the screen is a 1.60 times 10 to the negative 19 coulomb. So, and that is negative because we know electron is a negative, has a negative charge. then we will get if we punch this into our calculator, we will get this equals 6.25 times 10 to the 18. So that's a lot of electrons. Now, it is possible to transfer electric charge from one object to another object. Usually, electrons are transferred and the body that gains the electrons acquires an excess of negative charge. The body that loses electrons has an excess of positive charge. Such separation of charge occurs often when two unlike materials are rubbed together. There are many familiar examples of charge separation, as when you walk across a nylon rug or run a comb through dry hair. In each case, objects become so-called electrified as surfaces rub against one another. A classic physics example is when an ebonite rod is rubbed with animal fur. The rubbing process serves only to separate electrons and protons already present in the material. When an ebonite rod, which is a hard black rubber, is rubbed against the animal fur, some of the electrons from atoms of the fur are transferred to the rod. So the ebonite becomes negatively charged and the fur becomes positively charged. It becomes excess positive charges. So what happens in here, whenever an electron is transferred to the rod, a proton is left behind on the fur. Since the charges on the electron and proton have identical magnitudes but the opposite signs, the algebraic sum of the two charges is 0, and the transfer does not change the net charge of the fur rod system. So you can, if we count, we can see, let's say, if there are 8 electrons that are moved to, transferred to the rod, then the fur will have a charge of positive 8e, and the ebonite, or the rod, has negative 8e. So if we talk about the net charge of the system of the fur and a rod, that equals Q fur plus Q of the rod, which makes it positive 8e minus plus negative 8e. That gives you a 0. So the net charge of the system is 0. So to summarize this, if each material contains an equal number of protons and electrons to begin with, the net charge of the system is 0 initially and remains 0 at all times during the rubbing process. A great number of experiments have verified that in many situations, the law of conservation of electric charge is observed, which states during any process, the net charge of an isolated system remains constant or is conserved. It is easy to demonstrate that two electrically charged objects exert a force on one another. So let's consider two charges, a positive charge and a negative charge. So experiments show that when you put two charges that are oppositely charged, then they will experience an attractive force. They will get attracted to each other. Okay, so when you take two positive charges and put next to each other, you will see that these two charges will experience repulsive force. They just will repel from each other. Same thing happens if you take two negative charges. Negative charges, and they will repel. This behavior illustrates a fundamental characteristic of electric charges in general. So it says, like charges repel, unlike charges attract. So like other forces that we have encountered, the electric force, also sometimes called electrostatic force, can alter the motion of an object. It can do so by contributing to the net external force, some of the forces, and that acts on the object and then will contribute in the Newton's second law as sum of the forces equals ma. So electric force can go into the net force here. So therefore, if there are no other forces, but there is an only electric force acting on a charged object, then this charged object could accelerate because of the net external force. The electrostatic force that stationary charged object exert on each other depends on the amount of the charge on the objects and the distance between them. Experiments reveal that the greater the charge and the closer together they are, the greater is the force. To explain these features in more detail, let's consider two charged bodies. These objects are so small compared to the distance, let's say r, between them, that they can be regarded as mathematical points. So we call them point charges. And they have magnitudes of q1 and q2. If the charges have unlike signs like negative and positive, I should put the positive right here, okay? Then each object is attracted to the other by a force that is directed along the line between them. So we can draw these forces to go to the force that is, let's say, object 1 is experiencing due to object 2. So I'm going to write force 1 experiences due to object 2. And then we will have force that object 2 is experiencing due to object 1. In case we have same charges, like two positive point charges or two negative point charges, each object is repelled from the other one. So we're dealing with repulsive force. And the repulsive forces, like the attractive forces, act along the line between the charges. Whether attractive or repulsive, the two forces are equal in magnitude but opposite in direction. These forces always exist as a pair, each one acting on a different object in accord with Newton's action-reaction law. Of the French physicist Charles Augustin de Coulomb in 1700s, late 1700s, early 1800s, carried out a number of experiments to determine how the electric force that one point charge applies to another depends on the amount of each charge and the separation between them. His results are known as Coulombs Law, which states that the magnitude of the force, electrostatic force exerted by one point charge Q1 on the other point charge Q2 is directly proportional to the magnitudes of the Q1 and Q2 of the charges and inversely proportional to the square of the distance between them. Then as an equation, we can write this as a force equals some constant Q1, Q2 over R squared, where K is a constant, electrostatic constant or proportionality constant. And it is experimentally found to be equal 8.99 times 10 to the 9 newtons times meter square over Coulomb square, and that is in SI units. It is common practice to express the K in terms of another constant known as epsilon naught, and K equals 1 over 4 pi epsilon naught, where epsilon naught is called free permittivity of free space and has a value that is given according to 1 over epsilon naught equals 1 over 4 pi k, and that equals 8.85 times 10 to the negative 12 Coulomb square over newtons times meter squared. And sometimes Coulomb's law can be written as F equals 1 over 4 pi epsilon naught Q1 Q2 over R squared. Coulomb's law equation might look like more complicated in the form of epsilon naught, but other fundamental equations we haven't seen yet are simpler in terms of epsilon naught rather than K. It doesn't matter which form we use. Let's call it first one or the second form, they are equivalent. The latest precise value of electric charge and epsilon naught are given inside the inside your book. So it is also important to mention that these equations that represent Coulomb's law apply to objects whose size is much smaller than the distance between them. Ideally, it is precise for point charges. For finite-sized objects, it is not always clear what value to use for R as a distance between them, particularly since the charge may not be distributed uniformly on the objects. If the two objects are spheres and the charge is known to be distributed uniformly on each of them, then r is distance between their centers. So Coulombs law describes the force between two charges when they are at rest. Additional forces come into play when charges are in motion, and this will be discussed later in later chapters, the study of which is called electrostatics, that we're dealing with now because charges are stationary. So when calculating with Coulombs law, we usually ignore the sign of the charges and determine the direction of the force separately based on whether the force is attractive or repulsive.